Okay. Also, these the notes that I take, I'll make them available to you, but it is much, much better to take your own notes. Really. Uh, yeah, partly it will help keep you engaged because it's a long class, and so yeah, we'll try to take breaks and stuff, but certainly keeping your own notes and maybe reviewing them quickly during break time is a good way to catch where you're missing something, or you might have more questions about it, or you want more information, whatever. So please take your own notes. All right. I've also had issues sometimes with these recordings. Sometimes, I'm using WebEx. For whatever reason, sometimes the recording doesn't compile correctly. So the last time I taught, I think there were 2 lectures that there was just no recordings for. So that's another nice thing about being here live, and you don't miss anything. All right. So if it's okay with you guys, I'm going to turn off my webcam so I can pull my computer forward and start taking notes. I will keep looking over at the chat window in case anybody has questions, or you can always unmute yourself. Okay. I really encourage students to ask questions and also give me feedback if things are moving too fast or too slow or anything. Feedback is good. So first, we're going to be talking about probability. This will include what are called probability spaces. This will include things like conditional probability. It will include concepts like dependent or independent events. Just to note, independent events are very nice. These are better. Just the math is much easier. Dependent events, things can get very, very complicated very quickly. So there's a lot of times people will make an assumption about things being independent, even if they're not, because it's easier to work with. Oh yes, joint probability spaces. If you don't know these terms, it's fine. We're going to be covering all of them. Then we'll move on to random variables. And these are also called probability distributions. I kind of like the word probability distribution because it is a little bit more indicative about what these things look like. So, for example, these, maybe that's 0.4. So, well, actually here. There's discrete random variables and continuous random variables. For discrete, these are things like a Bernoulli distribution. So that is like a coin flip, heads, tails. 0.5 probability of heads or tails. Or the probability of a fair die. No, let's do an unfair die. People always want to think about the fair one. Maybe this This one prefers the number 1. So this is a die that's been weighted so that the number 1 will appear more often than any other number. So these are discrete random variables. For continuous random variables, so let's see, Bernoulli, a binomial distribution. Oh, one more thing. Sorry, this is actually 3, 2. We are going to talk about counting. So counting is, it sounds easy. I mean, counting, it's easy. 1, 2, 3, 4, 5, great. But this is counting combinations and permutations, especially. So this would be, for example, I don't know, I open up my fridge and there's a bunch of food inside. How many different dishes could I make given the food that I have? So can I make 10 dishes or 20 dishes? You know, like this is taking things and combining them. So it's considering different combinations. Permutations is something kind of similar. For combinations, order does not matter. So if I'm making whatever, tomato and eggs, well, then I can, there's no difference between tomato and eggs or eggs and tomato. Like, it doesn't matter which one I take out of the fridge first. They should be, that is a combination. A permutation is when order does matter. So this would be something like, you have 10 books, and how many different ways can you read these books? And so here it matters which one you choose first, which one you choose second and third and fourth. This is a permutation. The reason why we care about counting is because it helps you frame probability at times. Mainly that you want to count the number of successes divided by the total number of anything that can happen. And especially counting the number of successes uses these combinations, permutations. Right, so for random variables, we'll talk about discrete random variables. For continuous, we'll basically just talk about the normal or Gaussian distribution. And that just looks like a bell curve. And it has some mean value and some variance. The variance is this, it's pronounced sigma. It looks kind of like a 6. It's a Greek lowercase s. Whatever. So, for linear regression, it's important to be familiar with this normal Gaussian, because that's one perspective you can have on what these points, how to find a good line given some data. Another very nice thing about the normal distribution is something called measures of concentration. Measures of concentration. So what this is basically the difference between maybe these. Each of these might have the same mu, let's call it 0, so both of these are centered at 0, but the one on the left here is much more concentrated around the value 0, and the one on the right is much more spread out around the mean. Oh. You cannot hear my voice. Is it just you? Can you hear it again now? Or... Yes, you can. Aneri, can you hear? Aneri, you still there?
Hello.
Yes. Okay, great.
Now
you can. Okay, great.
Yeah.
Thank you. All right. Thank you for letting me know. All right. So, yeah, there's a couple of reasons to want to know about this normal or Gaussian function. One, for linear regression. Also, it's just a super, super common distribution. One of the reasons why is because you can actually turn any distribution into a normal distribution. That includes these discrete distributions. These you can turn into a normal distribution. And you do that by taking the average of averages. So you find the average once, and then you save that number. And then you find the average again, and then you save that number. And then you find the average again, and you save that number. And if you do that many times, then you'll notice that the average of averages, you know, once you have these averages, now you find the average of them, and then that will be this mu. And every time you take an average, things will be, will take this form. So, let's see. Any distribution into this. This is the law of large numbers. So in probability, this is called the law of large numbers. And that's a very, very useful thing to know, because oftentimes you don't know what the real average is, because it's some random process. But if you take the average of averages, and if you have a curve that turns into one that's very concentrated, then you can feel very comfortable that your calculated average isn't so far away from the real truth. Even if there's no way for you to know the real truth, you can be confident that you're very close to it, within some confidence interval. Great. So, right. Okay, then this is just sort of the course outline. Then we'll move on to linear regression. Here we'll talk about best fit line perspective and best fit family of Gaussians perspective. First, we'll talk about univariate linear regression. That's like the 2D plot. It's a 2D thing. There's points, and then you're drawing like a line. That's univariate. And multivariate is like the plane in 3D space or high dimensional space. It's still a line, but just a line in higher dimensional space. Multivariate linear regression. There's more stuff that we could talk about with linear regression. Things like dummy variables, things like even sticking with univariate linear regression, you can actually make very complicated lines. Not just straight lines. You can make very curved lines. And this is still linear regression. It's not linear in x, it's linear in the parameters of the equation. We might get there. All right. And then, yeah, a little bit of programming and stuff, I guess. You know, programming will be somewhere in here. I put programming in quotation marks because this isn't a programming class. Using Excel is fine. For people who want to know a little bit of Python, I guess I've had at least one student say that they might be more interested in that. So I can give some resources for that. And this is basically the next the next 5 weeks here. Oh, I should also mention for the I'm not doing any quizzes. Usually I do quizzes when I'm teaching in person. I think that it's a good thing to do. I'm not doing quizzes online because I don't like using this type of technology for that. Where I give you a quiz, you have a certain amount of time to finish it, and at least the software that Rutgers is using, like, you can look at webcams and stuff like this. I just am not doing any of that. Let me my video here real quick. Yeah, so I don't like monitoring online, you guys, beyond when we're in class and we're typing and, you know, unmuting and stuff like that. So that includes the final. The final will be something that I would expect you to be able to sit down and finish in 3 hours. That's the way I'm going to be designing the final. That being said, I am not going to be administering the final online and counting down the time. Instead, it will be a take-home final. You can use whatever resources you have at your disposal. So notes, previous lectures, other things on the internet that you might find, or whatever. I designed the final myself, so I don't think that you'd be able to find like directly answers to questions or anything. But yeah, maybe you can find like an example online that makes an idea click or whatever. So no quizzes, and the final will be take home. So you'll have about 24 hours to do it. As I said, it should be something that you should be able to sit down and finish it within 3 hours. But if you want a little bit more time thinking it over, then that's fine. Okay. So let's go ahead and take, I guess, a 10-minute break. and we'll come back at 7:15. Thanks, everybody. Okay, introduction to probability. First, let me do this. Yeah. So I want to give you a little bit of a background in probability, just the idea of probability. So probability is one of the newest areas of math that have been put to paper. Today, people talk about probability all the time. You know, probability of the weather, probability of getting a promotion, probability of your stock portfolio happening, whatever. But this is a fairly new concept. In fact, the way that, when the Romans were around, one of the ways that Roman soldiers would pass time is by playing dice. And they'd throw some die and people would bet on the outcomes. But nobody really thought about how to maximize their profit. Like, it was just a game. You make a guess, you throw the die, and then you see if you got it. And if you did, cool, you won some money. And we know this because they found, die from ancient Rome. But it wasn't until the 1600s that anybody actually thought about trying to come up with a principled way of thinking about these things. This is a guy named, Bayes was there, Bernoulli, Laplace. They started writing letters back and forth talking about it. And the way that they thought about probability is what we would call today the frequentist view. So there's two views of probability. There's the frequentist view and the Bayesian view. For most things, they're equivalent. But the frequentist view is, let's say, rolling a die. So if you roll a die, then you'll get some number 1 to 6. So what's the probability of getting a 1? Well, what you do is imagine doing an experiment many, many times and counting the frequency of occurrence. Here, when I say an experiment, that means you roll the die and you write down the number. So if you roll the die 3 times, then at most you'll see 3 numbers. So that's not enough. You can roll the die, if you roll the die 10 times, then you'll get a better picture, but still maybe you got like 3 ones. And so is it 3/10 of a chance for 1? It's not very accurate. But if you roll it 100 times, then things will be closer to 1/6 across the board. 1,000 times, it'll be even closer to 1/6. 1 billion times, then things will be very, very, very close to 1/6. And so you can sort of imagine this going on into infinity, and that's what the 1/6 means. That the frequency that you would see this over many, 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 many trials. A trial and an experiment here are the same thing. It's one roll of the die. This was the way that it was originally thought of. Later, Bayes came about, and his view was more about starting with a prior belief and updating your belief yes, that's right, i.e. On subsequent trials. So this is a different way of thinking about it, or thinking about probability, which is you might have an educated guess before you do anything. Or even if it's an uneducated guess, doesn't matter. You make some guess. And then you do a trial, or you run an experiment. And then you see the outcome of that experiment, and then see if you were right or wrong, based on your guess. If you're right, then you keep your guess, or you sort of reinforce it more. If you're wrong, then you might need to update your guess to match what you're actually seeing. So this Bayesian way of thinking is more of the way that scientists approach probability. They have some hypothesis, and then they conduct an experiment, and then they see if that experiment purports with their hypothesis or not. And then they do an analysis. Actually, that is what the analysis is. And then they might need to come up with a new hypothesis given this new data. And now with their new hypothesis, they run another experiment and check their prediction and maybe go through rounds and rounds of this. And after enough times, then you can be confident that your beliefs are fairly stable. Now, these are two big ways of thinking about probability. And it wasn't until 1930, in the 1930s, there is a Russian guy named Kolmogorov's axiomization of probability. So an axiom is sort of the bedrock of any math. So for algebra, you have things like adding 1 to any number will increase that value by 1. So starting with 0, if you add 1 to it, you get 1. If you have that and you add 1 to it, you'll get 2. If you add 1 to that, you'll get 3. And that's one axiom. Another axiom is if you add 0 to any number, you should get the same number back. This is the identity. 100 plus 0, same number, 100. For multiplication, the identity is the number 1. If you multiply any number by the number 1, then you'll get the same number back. These are axioms. And then once you have axioms, and there should be some kind of small list, Then you can do proofs. You can make a statement, and you can say this statement is true because if I take this axiom and that axiom and that axiom and I combine them together, then I'll get this statement. And so we might call that a theorem. And over time, then you can have theorems that are based on other theorems, but everything goes back to the axioms. And this was just never done with probability before the 1930s. So all of this notation, this way of thinking, I mean, this is less than 100 years old, which is kind of bizarre, because it seems like probability is so prevalent, but it's actually a very new area of mathematics. In particular, for probability, there are 3 axioms. I don't know if I just want to state them outright, or that's generally how probability classes are taught. They teach you the 3 axioms. Maybe I won't do that. Maybe I might come back to it. But I wanted to give you guys a little bit of a story time about where probability comes from and ways to think about it. All right, let me turn this off and continue. Great. So, probability is built on a probability space. This is a definition. This is called a probability space, aka a formal statistical model or there's another name. It'll come to me later. So a probability space is 2 things. And I'll say this many, 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 many times. So I'll repeat it again. A probability space is 2 things. A set of all possible outcomes. Here, these outcomes are called elementary events. So we represent this set as using this Greek letter omega. And these curly brackets here, that just indicates that it's a set of things. A quick note on sets. I won't keep this, but note. For example, omega coin. And sometimes I'll write a subscript like this to differentiate different things, but this would be, for example, heads and tails. Elementary events can be anything you want. E.g. numbers, words, pictures, whatever. Anything you want. So heads and tails, these are words. I could write H and T. I could write 0 and 1. I could do happy face, frowny face. I could they could be two different songs, whatever. The set. Another one would be, for example, a die. Actually, I'm going to write this a little different. I'll say face 1, face 2, up to face 6. Because I want to emphasize that they don't have to be numbers. They can be anything. Okay, so you have a set. Move this over. Keep it on the same page. Make it smaller. Great. Sorry, I have to try really hard to keep everything in bounds here. I can zoom out and stuff, but then when I print this as a PDF, if I don't keep it this screen width, then the PDF doesn't print very nicely. By the way, if any of you guys use OneNote, I can share this OneNote as well. These notes over OneNote if you like that. Otherwise, I'll print it off as a PDF. Okay. So a probability space is two things. First of all, it's a set of all possible outcomes. Then there is a function that maps events to numbers between 0 and 1. Such that all numbers add to 1. This is actually one of the axioms. This is one of Kolmogorov's axioms. The events have to add to the number 1. And they're between 0 and 1. No negatives. What does it mean for I'll go out with a minus 10% probability? That's nonsense. No. So it's a number between 0 and 1, and all the numbers have to add up to 1. I'll use the PR to represent this function. And that is to say, it takes the set and maps them between numbers between 0 and 1. This is just a mathematical notation that says this is the name of a function, colon is defined in this way. This is the domain, and it is mapped to numbers between 0 and 1. Let's see if I can change the color of this, actually. Nice. Make this a bit thinner. Perfect. Okay. Example. So here, example. Using the above two, the probability of heads equals the probability of tails equals 1/2. Or the probability of face 1 equals the probability of phase 6, which is equal to 1/6. Okay? By the way, usually you'll see functions written in this way, f of x with these parentheses. Here I'm using these straight brackets. It doesn't really matter. It's just a notational preference. If I'm working with non-probability functions, I'll tend to use the parentheses, but for probability, I'll tend to use these. You can write whatever you want. I just don't want you to get confused. Okay. Another thing is that when it's understood in context, then you can write this probability function in this way. But this probability function is different than this probability function. Sometimes, in order to emphasize that, you can write, this is the probability of the coin. And this is the probability of the die. Okay, so again, this is just using this subscript notation just to make things clear. Sometimes, most of the time, I won't write it because I think it should be clear from context. But when I don't write it, you should have in your head that it is there. This probability function belongs to this world, this particular set. So there's 6 items in this set, and so this probability has to map 6 different events. Okay, you can't have 5. You certainly can't have 7. It has to be exactly 6. And just to give you, I don't know, I'm going to beat the dead horse now. Let's say this is the coin, and there's 2 elements. That's heads. This is tails. And for the die, you can also write a set in this way. You can write it using this notation, or you can also write it as sort of points in a circle. So here you'd have phase 1, phase 2, phase 3, phase 4, phase 5, and phase 6. And the function, this probability function, maps things to the line between 0 and 1. What do I mean by map? That means that you can kind of draw an arrow, and here this would be a 0.5. And both of these get mapped to the real number line. Here, this is 1/6. And so for a fair die, all of these things map to 1/6. Okay, this in green, this is called a mapping, and hopefully it's clear now. Yeah, if I use some terminology or a notation or something that you don't quite understand, please let me know and I'll explain it. Right now I'm trying to be thorough. Okay, I guess this is the probability of the coin. This is the probability of the die. Okay, so you have to have 2 of these things. You can't just have the set. Lots of people make this mistake. I ask for a probability, space, and people will just give me the set. The set is meaningless without the probability function. This is something that can take some time to get used to. A die, for example, cannot be the number 1. A die is not 1. A die is not 2. A die is not 3 or 4 or 5 or 6. A die can have a probability of being 1. It can have a probability of being 2. But the die is this random, it's this object that exhibits random behavior. So you can tell me what the different outcomes are. 1, 2, 3, 4, 5, 6. But for probability, I also need to know what the likelihood of any of these outcomes is. Okay, so you need 2 things: a set and a function. Let's see if I can emphasize this somewhere. Let's do this. A set and a function. By the way, when I take notes for myself, I tend to use lots of colors just because I like it. If that's distracting or something, let me know, and I'll try to do it a little bit less. Great. Let's see. So I'm just checking my notes. I don't want to jump too far ahead anytime. Right. Okay. Move this over. Actually, I'll just delete this. If you've been here now, you get the idea. So we can keep things a little clean. Okay. Def. An event. Okay, here. So this is the letter epsilon. It looks like a backwards 3. I don't like using the letter E because later when we talk about expectation, it could be easy to confuse one for the other. In fact, even then, I'll usually write an expectation using this E. But in any case, when I write this, what I mean is that it's an event. It's a subset, and this is written this way. This is a subset that is that could include the entire set. All right. Okay. A quick note about sets. Maybe I'll do this. Things don't look so the same. Okay. For a set, You don't need repeats. Okay, here 4 appears twice. This is the exact same as this. 1, 2, 3, 4. Okay, these are the same. And so generally, it's a good idea to just write the set as simple as possible. So avoid repeats. That's not wrong to have more than one number. It's just wasteful, and it can be confusing. So there's no repeats. Another thing is that here, no repeats. This is also equal to 4, 3, 2, 1, which is equal to 1, 4, 2, 3, whatever. Order does not matter. Okay, you can write things in whatever order you want. Think of a set like a bag with stuff in it. And you can shake the bag up and things get rearranged on the inside, but it's the same stuff inside of the bag. So order doesn't matter. You can write it in n order if you want, but don't expect that order to mean anything. Maybe you prefer it because when you write it, it looks pretty to you or something, but there's no meaning to the order. Okay. So, also a subset. If you have a set of stuff, a subset is just some portion of it. That's a subset. This is a subset. You could also say, for example, yeah, whatever. So that is written like A in, this is omega, A and omega. So what's the difference between, let's say, A and this symbol, B and omega? What this means is that A cannot be the entire world. Here, B could be smaller than the world, or it could be bigger than the world. Let me do this. B. B could be this. Okay for B. A, without this line on the bottom, like of the C looking thing, it's not the letter C, it's a symbol for a subset. A could be, for example, this, right? Everything in the world minus one thing. This is as big as A can be. Okay. Also, there is this, 2 straight lines. This means the size, number of elements that comprise the set. Okay, so here, if this is omega, then the size of omega here is 4. All right, so that's just a notational thing. All right, so if you didn't know much about sets, I think that covers just about everything.
Could you explain the C underline thing for the subset?
Yeah. So think about it like in algebra, if you say A is less than B, or A is less than or equal to B, these are different because this means that A is strictly smaller than B. A cannot be equal to B. It has to be something smaller. Where here, A can be anything smaller up until and including B. And it's the same idea here. So here, A can be any sized set that's smaller than omega. Here, B can be any set including all of omega itself.
Okay, gotcha.
Yep.
Thanks.
Yeah. So it's the same reasoning here. Why one symbol with a line under it. I mean, it comes from this. But they don't use a less than here because it's probability. And you also talk about things being less than. So you need a new symbol. They use a symbol that looks like a C.
Gotcha. Okay, thank you.
Yep. All right. So here, an event, I'll still say the letter E. An event E is a subset of omega. For example, I could say that epsilon is an even face. So the probability of epsilon, so this could equal face 2, face 4, face 6. And this would be coming from the die. All right, so here we have a subset. This is coming from this world of 6 possible outcomes, but I only care about 3 of them. And these are the 3 that I care about. I can give it an English phrase, an even face. Okay, this is the set of outcomes, and here's a rule. The probability of an event is the sum of the probabilities of the elementary events that define it. Okay, this is Kolmogorov's second axiom. So you don't need to write this. It's enough. This is a rule. Okay, this is it's actually part of the definition of the event. Yeah. So an event is a subset, and the probability of an event is the sum of the probabilities of the elementary events that define it. So this is a definition, right? Sometimes there's properties, and we'll talk about some properties, but definitions you cannot argue with. A definition, you can define anything you want. But once you have the definition, then you must respect it. And so this is a part of the definition of an event. And this is one of Kolmogorov's axioms. So, given that this is a part of the definition, you don't need to write the probability function for the event. But just to be clear, the probability of event E is equal to the probability of phase 2 plus the probability of phase 4 plus the probability of phase 6, and each of these are 1/6, which equals 1/2. Okay, so the probability of rolling an even number on a fair die is 1/2. Right now we're thinking about this. Everybody starts off with coins and die because they're easy to think about. Right now I want you to understand the notation and to understand the steps, because when you're dealing with more complicated probability spaces, then you can go back to the basic math that is behind it. So don't just ignore this stuff thinking, oh, well, that's so super obvious, I don't really need to remember it. I'm introducing stuff that's super obvious so that you can be comfortable with the fact that in basic situations where you already have a good intuition, how to arrive at the same answer going through some math steps. When things get more complicated, your intuition, I promise you, will fail you. That's one thing that I want all of you guys to walk away from this class knowing, that in simple cases, humans are okay at probability. But if you step even a little bit away from the simplest cases, you will have an intuition, but there's a very good chance your intuition is bad. It's wrong. So don't rely on your intuition. Rely on the math. If you have enough practice with it, then you'll develop a new intuition, and then you can find it a little bit more reliable. But I will present a couple of examples of when your intuition is bad. Actually, we'll probably spend about an hour discussing just one example of this. Not today, though. For today, we're just teaching you the basics. So, all right. We have an event. Generally, when you talk about probability, you're talking about the probability of a particular event. Oh. Let me move this down. I have a note that I want to say as well. Keep using this purple color for oh. Note. A probability space describes exactly one realization of the experiment. Let me do this a bit differently. Make that black. I'll do this. Okay. So, a probability space describes exactly one realization of the experiment. So, here, rolling a die or flipping a coin. This probability space here, along with its function, describes flipping a coin one time. If I ask about flipping the same coin 2 times, you need another probability space. You cannot use this one. This one is about flipping a coin once. Okay? So what if we wanted to talk about flipping a coin more than one time? Yeah. This is called a joint probability space. Where here, omega 1 is equal to omega 2. How do I do this? I'll say joint equals omega 1 cross omega 2 cross however many events you have here, n. Oh, one thing I did forget about sets that now it's important to know. Set multiplication. So that's the symbol for multiplication. And so there's number multiplication. But what about heads, tails? By heads, tails. What does multiplying here mean? Set multiplication is finding all possible combinations or all possible pairs. Combinations is slightly better than pairs. So what that means is that this is equal to heads, 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 tails. That is heads, 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 tails, and tails, heads, tails, tails. So that and this. Heads, you take the first one and you pair it with everything else. Then you take the second one and you pair it with everything else. Let me call this omega 2 flips. And this equals omega coin times omega coin. Okay? So that's what I mean here. Here I'm just doing 2 coins. But I could imagine flipping a coin n times. In fact, that might be good practice for you. What would it look like to have omega of 3 flips? That's good practice for you. I'll say one more thing and then we can take a break, which is This is half of it, right? Now we have a set. But this is a joint probability space. The joint here just means more than one. Probability space is two things. It's a set and a function. So far, I've just talked about the set. So how about the function? They keep examples in green. Example. No, I should have kept space there. Oh, I have a notational comment too. I'll get to that after break. Here, for epsilon in, yeah. Oh God, how to write this concisely. Okay, I'm sorry. I don't know of a way to write this concisely. So what I mean here is that this is here. That's the set of this world, okay? The first world. Times the set of the second world times to the set of the nth world. Okay, so I'm writing in the blue subscript here the world that that it's coming from. Okay, and the worlds can be of different sizes, so that's why I'm using the letter L and the letter K, because maybe in the case of flipping a coin, fine, it's the same over and over and over. But maybe I want to flip a coin, then I roll a die, then I draw a card from a shuffled deck, and so the coin world is going to have heads and tails as an event. The die world is going to have 6 things for its 6 elementary events. The deck of playing cards is going to have 52. And so these can be of different sizes. Now let's say that E equals E1, E1, E1. So this is going to be the first event. So taking the first event from the first world with the second event of the first event of the second world, with all the way down the first event of the nth world. If E, then the probability of E in the joint world is equal to the probability of E1. So the probability that the first thing happens in the first world times the probability from the second world of the first thing from the second world happening times the probability from the nth world of the first thing happening in world n. Sorry, I know that this is about as complicated as notation as we're going to get. I don't know of another way to do it that is correct. So, yeah. Just as a quick example, and this is a part of the definition as well. This is a definition. So the probability of heads equals the probability of tails equals 1/2 times 1/2, which is 1/4. Okay, that's where you get the fourth probability of seeing two heads in a row. You cannot talk about getting two heads in a row in this world, because there are no two heads. You get one heads. That's it. This is one flip. All right? The probability space describes one realization of the experiment. So if you want to talk about two heads, then you have to construct a new world. And we can use the original world, the one, but then we just, we use it to then construct a new world. And the probability of any of these events is defined in this way. You take the probability of the first thing in the first world times the probability of, in this case, the first thing in the first world, or the second world, and on and on. Okay. Let's stop here. Let's take a, I don't know, what do you guys want, a 10-minute break, 15? Great. All right, so let's come back at 8:25. We're setting up the rules for probability. The way that I would like you to think about this is as a probability being a set and a function. You need both. And a probability space describes something happening one time, and that's it. You can consider things happening many times, but then you just need a new space. Most of the time when talking about probability, people are more interested in events. So a subset of all possible things that can happen. So not one individual thing happening, but of some combination of them. For example, rolling a die, maybe you care about getting an even or an odd number. the probability of an event is the sum of the probabilities of the elementary events that define it. And we left off before break talking about joint probability spaces. This is just when you combine probability spaces together to form a mega space, like a space that combines different worlds together. And there's a very fixed way that you do that. First, you take all possible combinations of all of the events, and that defines the elementary events in the joint probability space. And for any elementary event in this new mega space, the probability of that happening is the probability of an event happening in World 1 times whatever event happens in World 2 times whatever happens in all of the worlds. I mean, you get to choose one event from each world. You have all combinations of them, so you haven't missed anything that could happen. And the probability is just all multiplied together. So the probability of one event from the first world times one event in World 2, and you just multiply these. So you don't really have a choice in how to design this. Everything is just fixed. So you figure out which worlds you want to combine, and follow the rules for coming up with the new list of events that is happening in this combined world. The probabilities, also you have no choice. These things are all definitions. This is one concrete example of taking a world of flipping a coin once and constructing a new mega world that is flipping the coin twice. And so here you have 4 elementary events, and the probability of any of those 1 events happening in this example is 1/4. I want to make another notational comment. These things. Here, I'll just highlight the whole thing. This is one event in the New World. It's one event, and the way that I'm using notation to show that is that I wrap it in parentheses. Okay, so this is one thing. Here's another set of parentheses. That's another one thing. You could, earlier, when we were talking about, the world of heads and tails and the corresponding probability function, you could write it this way. The probability of heads equals the probability of tails equals 1/2. So here I'm using the parentheses. But most of the time, if it's just a single item here, people will just get rid of the parentheses. So these are equivalent. I will tend to not have the parentheses for single things. When you have joint probability spaces, it's kind of required. To define one event as being comprised of other smaller events. But it's one event. Okay. I would like to take a moment and just ask how you guys are feeling so far. Everything going at an okay pace? Too much notation? Did I lose you somewhere? Yeah, anything. All good. Excellent. Good. All right. All right. Um, so we're still going to get through some definitions. Um, um, I leave this to you for practice. So what would this thing look like with 3 flips? So in the 2 flips example, is the probability of omega equal to the probability of heads? Right. So your question is this. Here, is it the case that the probability of this omega 2 flips, by the way, congrats on finding the omega. Yeah, you can just type O or omega, or yeah, write it like that. That's cool. Your question is, does this equal the probability of heads times the probability of heads tails dot 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 times the probability of tails? No, it does not, because this would equal 4 to the 16th. What is that? 2 squared, 2 to the 8th, 256. That would equal this number. That is 1/4 times 1/4 times 1/4 times 1/4. So that's not the way it works. Instead, you add these together. And so this equals 1. So the probability of any world has to equal 1. Yeah, here you add probabilities, you don't multiply them. Let me make a quick note here. Yeah, side note. No, I'll keep that, actually. I'll erase it in a minute. Okay. English versus math. So, there is a very strict meaning of ors versus ands in probability. So The result of 2 coin flips will be heads, 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 or heads, tails, or tails, heads, or tails, tails. Here, ors correspond to addition. If this or that is something we're discussing, then the probability of this or that, you sum the probabilities together. When you talk about ands, like I flip the same coin twice. What is the probability of H on first flip and H on second flip? This is the probability of heads on the first flip times the probability of heads on the second flip. And here, the first flip and the second flip are 2 different worlds. And so this is equal to a half times a half, which is equal to 1/4. So when you're talking about one event and another event and another event, or this thing happens and then this other thing happens and then another thing happens, you're going to be multiplying these probabilities together. If you're talking about this happening or that happening, you're going to be adding them. You could also talk about this and this, or this or that and that. So then this is some combination of pluses and multiplications. Multiplication. So this is a good thing to sort of have in your head when you're trying to work through the probability of certain things happening. The way you say it in English, and then the way that this works out with the math. Oh, so here, the result of 2 coin flips will be heads, heads, or heads, tails, or tails, tails, or heads, heads. So that's the probability of HH plus the probability of everything up to and including the probability of tails, tails. And so this equals 1. And so this should always be true. Take any world. Let's go back up here. For the coin, what's the probability of getting heads or tails? Well, one of them has to happen. So the probability of getting heads or tails has to be 1. Same thing with the die. What's the probability that the die is face 1, or face 2, or face 3, or face 4, or face 5, or face 6? It's 1/6 plus 1/6 plus 1/6, and you have 6 of them, so that also equals 1. You could say, what's the probability of face 1 and face 2? Here, the probability would be 0, because this doesn't exist as an event that can possibly happen. Anything outside of the set of events is going to be probability 0. There is no face 1 and face 2 on one roll of the die. Good questions. All right. Yes. Now we have another definition. Independence. Here I'd like to call on somebody. How about, I don't know, Jenny? Do you have a mic?
Yeah, I'm here.
Hey. What do you think it means for two events to be independent from each other?
I would say that it just means that it doesn't, like, either one doesn't impact the other.
Either one doesn't impact the other. Very good. All right. So there's two definitions. A and B are independent if, just another notational thing. This means if and only if, whatever, one. We'll need to talk about conditional probability, but this is the way of writing what Jenny said. That the probability, this line, I'll talk about this right after, conditional probability. This means the probability of A given B. That's the way it's read. So the probability of A given B is equal to the probability of A. That is that maybe B happened, maybe it didn't. It does not affect the probability of A. So this is one definition. There's another definition, which is the probability of A and B is equal to the probability of A times the probability of B. Simple enough. I think the first one makes more intuitive sense. Most of the time people will say something like that. Oh yeah, B has no effect on A, or yeah, knowing about B doesn't change A, whatever. This is a little different, although they're equivalent. These two things are the same. How about Brian? Do you have a mic?
Yeah.
What's an example of an independent event? Or two events that are independent of each other?
Let's see. Let's see. Ticket sales for a football event, and let's say I don't know. I'm kind of getting stuck on this, even though it's a pretty easy question.
Okay, how about ticket sales for a football event and the price of Coca-Cola?
Sure.
Okay, so why would those be independent?
because they don't affect one another.
Yeah, if ticket
For sure.
prices or ticket sales go up or down, doesn't really change the price of Coca-Cola. Also, if Coca-Cola has some, I don't know, price change, that's probably not going to be the thing that affects ticket prices. Okay, so how about Brian? Yeah, same thing. How about dependent events?
Let's say ticket sales for a football event and the weather.
Very good. Excellent. Yep. Perfect. um, let's see. Right. So, okay. I like to try to give multiple different ways of thinking about probability. Sometimes one of these ways might resonate with you more than others. Other times for me, when I'm doing this kind of stuff, it depends. Sometimes I like to think about it one way, sometimes I'll think about it another way. Just depends. So having multiple different viewpoints to go back and forth from are useful sometimes. In particular, using pictures. So here I'll do the world of the coin, and here I will do the world of the die. So the way that you use this picture is that this is area 1. Okay, this whole thing, it's a block of area 1. It's a 1 pound block, or a 1 kilogram block. And then when you divvy it up, then whatever fraction of that defines its probability. So here, heads and tails each take up half of the block. So the block is 1, I'm cutting it in half, therefore this thing takes up half and this thing takes up a half. If I were to do this with a die, then it would be something like this. Okay? So then the way that you can think of events are that you just highlight, I guess, or fill in, or whatever, the events that you care about. So let's say, here's one event. The event of the die being greater than 3. So what's the probability of that? Well, it's the probability of phase 4 plus the probability of phase 5 plus the probability of phase 6, which is 1/6 plus 1/6 plus 1/6, which equals a half. You can also just tell that this yellow thing is taking up half of the area. So, probability of face greater than 3. That's this yellow one. Okay, how about, here's another event. The probability that I get a 5. Probability face 5. let's make it clear. So are these dependent or independent? This is the kind of thing where this type of approach is maybe a little bit harder, because we don't have any conditional probabilities. We just have individual probabilities. So we can check this, though. The probability of A and B, that's this green region. It's the yellow plus blue. What's the probability of A? Well, maybe that's the yellow one. And the probability of B is this, 1/6. So the question is it true that the probability of face greater than 3... I'm sorry, hang on just a second. Thank you. Yeah, which of these two definitions do you use? It depends. Sometimes you can use them both, sometimes you can't. In this example, this one, we have to use the second definition because we don't know any of the conditional probabilities. Sometimes you only know the conditional probability, and you don't know, for example, the probability of B happening by itself. So then you're kind of forced to use this one. Other times you have more information, and then you can use whichever one you want. For this, the first definition, I myself find it a little bit more intuitive. The second definition, I end up using it more often. So, yeah. So, hold on. Which implies dependent. Okay. So let's take we'll call it a 10-minute break and 15-minute break. And then we'll come back and I'll talk about conditional probability. This is a very good point for that. So thanks, everybody. Sorry, thank you. Yes. Right, I was just saying that we were just talking about independence, and one of these definitions relies on this idea of conditional probability, which we hadn't defined, but that you already have some kind of intuition for. I mean, insofar as maybe your first feelings about independence are, well, one thing doesn't affect the other. And in this notation, the probability of A given B is the same as the probability of A. The probability of A doesn't change given B. So the definition is probability space. This is important, that when you're talking about a conditional probability of events A and B, they have to be from the same probability space. That might be a joint probability space that you make. For example, the probability of rain today and the probability of certain ticket sales. Those are two separate probability spaces, but you could make a joint probability space from each of those, and therefore A and B would be coming from that joint space when weather and ticket sales are both combined together as far as the events that can happen. Here, the probability of A addition on B equals the probability of A and B divided by the probability of B. Okay. Yeah. So here, up above this picture, A, the probability of A is the percent of A inside of omega. Likewise for B, and likewise for their intersection. Here, this green part, this is the percentage or the fraction of A intersect B inside of omega. Quick notation note. Okay, so a set intersection is like this. This is where A and B overlap. A union, it would be the union between A and B is the area of both of them added together. Fine. And this is... yeah. So I want to keep this picture in here. Great. So, first of all, the probability of A and B, that's easy enough. That's just this intersection. So the probability of A given B brings in the probability of A and B both happening. That makes sense. Why divide by the probability of B? The way that I think is useful to think about this is that let me go here. We have A and B and omega. Okay, omega is the world of anything that could happen. All right, so this is the intersection between A and B. All right. Now, when I say the probability of A given B, you could also say the probability of A conditioned on B, or knowing that B happened, what is the probability of A? So let's take that last phrasing. Knowing that B happened, what's the probability of A? Well, now that I'm telling you that B happened, we can have a new world. This becomes our new world. Right? We can erase everything outside of it because I'm telling you that B happened. Therefore, only things inside of B matter. And this part is the part of A that overlaps B. And this is the only part of A that we could consider. So if this fraction inside of B, so dividing by the probability of B is when I just erased everything. It's sort of rescaling the world. Remember before, here, whatever, A omega, the area of this, the area of everything is equal to 1, right? Because it's a probability space. So if I want to consider a new world, or a smaller world, because I'm telling you that B happened, now B, this was originally, B was the fraction that it occupied in the world. But now we want to readjust this. Say this is 1/3, okay? The probability of B. Right now it takes up 1/3 of world omega. But now if I want to make this the new world, it needs to equal 1. How do I get it to equal 1? I can divide it by 1/3, and then that equals 1. Great. So that's what this is. You divide by the probability of B because now B becomes your new omega. B becomes the world that you care about. And so you have to scale everything. And you scale it by dividing by 1/3. Everything by 1/3. When you divide B, your world, by 1/3, well, now you're making it equal 1. So it's a good probability space. And this part is the probability of A and B. This is the part of A that is inside of B. Okay, it's there. It's the intersection. All right. Great. Let me see if I can't make this a little better. So these are the things that are going to be going away. Okay, I hope that makes sense. So that is what a conditional probability is. Or this is the way that it's defined. Now, let's take an example. Given an roll of a fair die is odd, what's the probability of it being face 1? I'll give you guys a couple minutes to think about this. I'd like you to have an answer and then walk me through it. So I'll give you 2 minutes till 9:35. Great. Jake, where are you getting a 1/3 from?
Well, since it's already given that the roll of fair die is odd,
Mm-hmm.
we have 3 options: 1/3 or 5. So it's just 1/3.
Great. Yeah. So you have 1, 2, 3. Actually, I'll do this way. 1, 3, 5, 2, 4, 6. So this is the original world. You're saying that now you know it's odd. Oh, and these are all probability 6th. Oh.
Yeah. So it's all 1/6 to begin with.
Yeah, so these are all probability 6th. Then you're saying, well, now you know it's odd, so this part of the world disappears. And now there's 3 choices, each with a probability of 1/3. The reason why it's 1/3 is because you're multiplying everything by a half. Or, I'm sorry, you're dividing everything by a half. So, 1/6 divided by a half is 1/6 times 2, which is 1/3. So then these probabilities also have to be updated now. All right, and the probability of 1 is 1/3. Very good. Excellent. Okay. That's enough for conditional probability for now. There's one last thing that I'll teach today, and then we can end. Actually, where was that? All the way up here. In the beginning, I was talking about the frequentist interpretation of probability and the Bayesian interpretation of probability, where the Bayesian, the frequentist one, you're counting frequencies, imagining in your mind doing an experiment a million times, a billion times. Just some huge number that approaches infinity, whatever. The Bayesian approach is about having a prior belief and then updating your belief. So you start believing one thing, and then you do a bunch of experiments, and with each experiment, you update your belief. So I would like to talk about, now this is a theorem. This is the first thing that we're running into that is not a definition, it's a theorem. And this is Bayes' theorem. This theorem is the probability of A given B. We talked about one definition up here. This is a different definition. This is the probability of B given A times the probability of A divided by the probability of B. Okay, so why am I calling this a theorem and not a definition? So again, theorems come about by taking axioms or definitions and mixing them up together to come to a conclusion. And whatever conclusion you reach, then that's the end of the theorem. So we can prove this. Here's the proof. By definition, we know that the probability of A given B is equal to the probability of A and B divided by the probability of B, right? We just talked about it. That's the definition, one, of conditional probability. Likewise, I could say, by definition, the probability of B given A is the probability of A and B. But now this is scaled by the probability of A. All right. Now, by algebra, the probability of A and B is equal to the probability of A times the probability of B given A. That is coming from here. Right? I'm just taking this probability of A and I'm moving it to one side. Right? So the probability of A and B here, that's equal to the probability of B given A times the probability of A. Fine. Now, this is 2. This is 3. Rewrite 1 using 3. So here, the probability of A given B is equal. Now this one, the probability of A and B on top, I'm just going to rewrite it with this. They're the same thing, right? So, copy, paste, paste. And of course, all of this is over the probability of B. A black box here just means the proof is finished. Okay, there. So I'm using definitions of stuff, I'm using algebra, and I'm rewriting things to arrive at a conclusion. So that's what makes this a theorem. I can state that this is true, and this is true because I can prove it. I don't know if you guys have much experience in proofs. Maybe you did some in geometry or something, or maybe other classes. I don't know what classes you've taken. This is an example of a proof. So we can pick a little bit more of this up the next class, but why, I want to at least say, why does this lead to a new interpretation of probability? The Bayesian interpretation. Well, let me take Bayes' theorem, this. Here, I'll just write it again. Oh, what's that? So the probability of A given B equals probability A times probability B given A all over the probability of B. Okay, I'm just rewriting, I'm writing the same thing as above. So, especially in science, people might be, they would like to know what's the probability of my hypothesis, or the probability of a hypothesis, given the data that I have. Okay, so let's just replace the A's with evidence or hypothesis. So this is equal to the probability of my hypothesis just by itself. Okay, my prior belief. In fact, this is called a prior. This is my prior belief about my hypothesis being correct. Without knowing, without even looking at the data. I have a prior belief about it. Now, what's the probability of the data given the hypothesis? If I tell you that my hypothesis is true, then what's the probability that you see this data? And then you divide it all by the probability of the data itself. Like that the data is just going to independently just happen. So, for example, melting ice caps. I have a hypothesis of global warming. Now I have some new data about melting ice caps. Well, what's the probability? What do I currently think right now about the probability of global warming? Okay? Well, if global warming were true, then what would I expect what would be the probability of this melting happening? Is it a high probability, low probability? Whatever. And then what would be the probability that ice caps melt? Sometimes. Maybe it's just a very normal thing. Every year or, every decade, there's melting and then freezing and then melting. Like maybe the probability of that is really high. And then a big number in the denominator makes this probability small, which means that my hypothesis doesn't change much, or my hypothesis doesn't really do anything about explaining the data. Okay, so this is more of a science-y way of thinking about it, and this is the way that actually science works. But yeah, this is the reason why there's this idea of having a prior belief and being given some data the way that you update your belief. This is how you walk away with your belief. Does the probability of your hypothesis go up seeing this data, or does the probability of your hypothesis go down? That's as much as I'll say about that. It would be maybe a fun thing for you. I don't know. Oh, maybe it's fun to sit down and try to think of an example of this, updating your beliefs about something. You think that something might be true, you try to find some data, or you collect some data, and then you see how your belief is adjusted. So that's it for today. I think we can end a little bit early. Honestly, it seems a little masochistic to have a class from 6 to 10 p.m. But there is a lot of information to cover, and we don't have so long together. So hope you guys have enjoyed the class. I'll stick around if you have any questions. Of course, you can always email me. I will upload this lecture to YouTube. I'll share the link, and I'll put these notes on Blackboard along with a reading. The reading is something like 30 pages. It's covering a lot of the things that I am in this class, especially in the this first week. It also goes into some more stuff that's a little bit more math heavy, although you can understand any of it. And as I said, it was written by a Rutgers professor for Rutgers students, and I have his permission to share it. So that's it. Thank you, everybody, and I will see you on Thursday.